Awesome. So it is my pleasure to introduce our very first all-alumni reading event speaker who will here telling us about her super awesome book, and for an author Q&A, Dr. Nicole Yunger Halpern is a theoretical physicist and currently a fellow of QuICS, the Joint Center for Quantum Information and Computer Science at the University of Maryland, and is also a theoretical physicist at NIST, the National Institute of Standards and Technology. She has far more in her bio than that, but I'll turn it over to Nicole now to tell you a little bit more about her quantum journey and what led her to starting this book.
Great. Thanks very much for the introduction, and thanks to everybody for joining. I was really excited to partner with Qubit by Qubit. So I'm going to start by talking about some of the main ideas in the book and what quantum steampunk is. And then we're going to have time afterward for a question and answer session. And at that time, feel free to ask me anything about careers or quantum science or just anything else you're interested in here. So since you are a Qubit by Qubit audience, I know that this group is on the sophisticated side, so I can be a little bit technical. So I'd like to start with a technical term, namely steampunk. So steampunk is a genre of literature, art, and film. Steampunk works take place in the Victorian era, the 1800s, when the Industrial Revolution has been humming, London is full of smog and Sherlock Holmesian mysteries, railroads are cutting across the American West for the first time, and people wear waistcoats or petticoats. Against this backdrop are futuristic technologies, automata, time machines, flying ships, and submarines. You might have encountered this steampunk novel, The Time Machine by H.G. Wells. It was written during the 1800s, but steampunk is very much with us still. The Invention of Hugo Cabret was a New York Times bestseller in the early 2000s. Enola Holmes was one of the first films that debuted on Netflix due to the pandemic. It follows Sherlock Holmes's little sister, Enola. The film was a hit. I loved it, I suggest it, and the sequel is coming out soon. Then The Nevers is a show on HBO about Victorian women who have supernatural gifts. These works reach back to the past and ahead to the future. This fusion of old and new creates a wonderful sense of nostalgia and adventure and exploration. So fans dress up in these steampunk costumes with top hats and goggles and gears and gather at steampunk conventions. But what used to be a fantasy of steampunk has become a reality in my field of research. I'm a theoretical physicist, and I work at the intersection of three fields: quantum physics, information science, and energy science. So I'll briefly preview this intersection and then discuss it in more detail. Information science is the study of how efficiently we can process information. Quantum physics is the study of the very small, such as single atoms and ions. They behave in counterintuitive ways that everyday objects can't. Scientists and engineers are now leveraging these counterintuitive behaviors to build quantum computers, which will be able to process information in ways impossible for familiar technologies such as my laptop. Thermodynamics is the study of energy. It was developed during the Victorian era to describe the work performed by one of the cutting-edge technologies of the century, the steam engine. Today's cutting-edge technologies include quantum devices, which are very, very different. So we need to re-envision the thermodynamics of the 1800s for the 21st century. In other words, we need to reach back to the past and ahead to the future to ask how quantum engines would look and what they can achieve. So a genre of science fiction is coming to life at the intersection of quantum physics, information science, and thermodynamics. Let's look at each of those components more closely. Information science is the study of how efficiently we can perform information processing tasks. Those include solving computational problems, like calculating a satellite's trajectory, communicating information, such as over the web, securing information cryptographically, and storing information in memories. We live in the information age, but what is information? It's basically the ability to distinguish between alternatives. Say that a friend of yours asks whether the tavern down the street, because of course you are in Victorian London, is open or closed. So you peer through the window and see either filled cups and plates or clean dishware stacked on the counter. You've gained the ability to distinguish whether the tavern is open or closed. You've gained information. We measure quantities in units, such as seconds or teaspoons. So what is the basic unit of information? It's called the bit. It's the amount of information you gain if you have no idea of the answer to a yes or no question, and then you learn the answer. Say that the tavern down the street has a probability 1/2 of being open and a probability 1/2 of being closed. When you peer through the window, you gain a bit of information. We can encode a bit in a physical system that can be in one of two possible states. In a familiar computer, a bit is encoded in a transistor that has the value 1 or the value 0. I realize that you might know much of this material already, but I'd like to ensure that we're all on the same page. Quantum physics is the study of very small things, such as single electrons and atoms and particles of light, which we call photons. These systems behave in ways impossible for everyday systems, such as books and microphones and human beings. Everyday objects are large, are massive, and contain many, many particles. They're called classical. So quantum physics is non-classical. What are our favorite counterintuitive quantum behaviors? We can begin to grasp one by supposing that some young physicist, let's call her Audrey, has an electron, and her brother Baxter has another electron. The two siblings can perform some operation on the particles that creates entanglement between them. Entanglement is a relationship that quantum particles can share and classical particles cannot. So here's, at least in part, how I think about entanglement. Suppose that Audrey measures some property of her particle, and the measurement has two possible outcomes, which we'll label 1 and 0. For instance, Audrey can measure whether her electron has a lot of energy or just a little energy. If the two particles are entangled as strongly as possible, then Audrey will have no idea which outcome she'll obtain. 1 and 0 have 50-50 chances. Now, suppose that instead, Audrey measures her particle and Baxter measures his. Now the siblings can predict something about the joint outcome. In one example, if Audrey obtains a 1, she'll know that Baxter will obtain a 0. And if Audrey obtains a 0, she'll know that Baxter will obtain a 1. Furthermore, there is measurements that the siblings can perform jointly on the pair of particles together, such that they can predict the outcome with certainty in advance. So there's some information that isn't in Audrey's particle, it isn't in Baxter's particle, it isn't in the sum of the particles addressed individually. It's spread out across the pair. But when it comes to entanglement, the whole really is greater than the sum of its parts. Scientists and engineers are now leveraging entanglement in quantum information science. I know you've studied some of this. Quantum information science is the study of how we can use quantum phenomena to process information in ways forbidden for classical systems. Quantum computers, which we're building now, will be able to solve in minutes certain problems that would cost even supercomputers many years. An important application will be research and development in material science and technology. For instance, in some countries, food security is at crisis levels. So fertilizer is extremely important. We invest about 3% of the world's entire energy output in producing fertilizer. Why do we spend so much energy? Because we produce fertilizer using an old technique from 1909. bacteria can accomplish the same goal much more efficiently. But those bacteria use a molecule that's too complicated for us to simulate on classical computers. However, the molecule is quantum. So a quantum computer will naturally be better suited to unlocking the molecule's secrets. And if all goes as we hope, then potentially transforming fertilizer production and energy use. Little wonder that governments are pouring funds into quantum science and technology. So our companies, including Microsoft, which has an advertisement I'm showing here, Google, IBM, Amazon, Honeywell, and many brand new startup companies. Now, this object belongs to IBM. This is not a quantum computer, even though it looks cool enough to be one, doesn't it? Actually, many people think this looks steampunk. But this object holds a quantum computer which fits on a small chip. The chip needs to be at low temperatures to support quantum behaviors such as entanglement. So this device cools the quantum computer to temperatures lower than that of outer space. Now, cooling leads us to the third element of our triumvirate, thermodynamics. Thermodynamics is the study of energy, the forms that energy can be in, and the transformations amongst those forms. Objects can transmit energy in two forms, heat and work. Heat is the uncoordinated energy of particles jiggling about randomly. Heat is disorganized and so not directly useful. Work is coordinated energy that can be directly harnessed to power a factory or raise an anchor. Heat engines convert this random heat into coordinated work. Heat engines drove the Industrial Revolution by powering the first factories. People started wanting to know how efficiently engines could operate. So they developed the theory of thermodynamics, giving it a practical bent. But the practical questions led to fundamental questions like, why does time flow in only one direction? Or do materials really consist of particles too small for us to see? Now, cooling, expelling heat, is a thermodynamic process. But how do you measure the heat emitted by a quantum system that's cooling down? You can measure the heat emitted by a classical system by measuring the system's energy, cooling the system, and measuring the energy again. The initial energy minus the final energy is the heat lost. But quantum systems are more delicate than classical systems. You've probably heard of Heisenberg's uncertainty principle. Werner Heisenberg was a German physicist who helped found quantum theory during the 1920s. He intuited that if you measure a quantum system, you disturb it. If you measure a quantum system's energy, you can change its energy. So how we can measure quantum heat, or even conceive of quantum heat, is not clear. Furthermore, this fridge here is a large classical system. Could we build a fridge from a quantum system? How small could we make it? More broadly, just as there are information processing tasks, such as encrypting information, there are thermodynamic tasks, such as refrigerating. Given that quantum phenomena benefit information processing tasks, can they benefit thermodynamic tasks? How can we extend the Victorian theory of thermodynamics from large classical systems, such as steam engines, to small quantum and information processing systems? These questions underpin quantum thermodynamics, my field of research. This field shares its aesthetic, its spirit with steampunk, which is why I call my work Quantum Steampunk. Quantum thermodynamics stretches back to the 1930s. During the 1950s, researchers designed the first quantum engine. It consists of one atom, which you can use in a maser. A maser is like a laser, but it emits microwave radiation instead of visible light. Turns out, an engine doesn't need gears and cogs and other moving pieces. It needs only one atom. Over the past decade, quantum thermodynamics has experienced a boom. Here's a photo from my community's big annual conference in 2018. That year we met in Santa Barbara, that's why the scenery is gorgeous. Why has quantum thermodynamics been booming? Because quantum information science matured during the early 2000s. It now offers a mathematical and conceptual toolkit for understanding quantum systems through how they store and manipulate information. Also, labs achieved exquisite control over tens to hundreds of thousands of atoms, ions, and photons. We've been using all of these tools from quantum information science to build and test a theory of quantum thermodynamics. Here's an example. We'll start with a classical story that showcases the interplay between information and energy. Then we'll see what quantum physics adds. We can store a bit of information, not only in a transistor, but also in a gas particle in a box. Suppose that the particle is classical, like a miniature basketball. This particle is a really, really simple gas. By the way, this illustration is by Todd Cahill, who is a steampunk artist. He had no experience with quantum physics whatsoever, but he managed to make gorgeous illustrations for my book, including this one. If the gas particle is on the box's right-hand side, we'll say that it encodes a 1. And if the particle is on the left-hand side, we'll say that it encodes a 0. Suppose that we have no idea where the particle is. It can be anywhere in the box. The position is totally random. Suppose that we want to reset the particle's position to the box's right-hand side, a nice, clean state. This is like taking a messy sheet of scrap paper that's been scribbled on totally randomly and erasing it to a nice, clean state. To erase the bit encoded by the gas, we let the gas exchange heat with its surroundings, which have a fixed temperature through the box's walls. Then to reset the gas's position, we slide a partition into the box near the left-hand wall and push the partition to the box's center. Now the gas is trapped in the right-hand side. At what cost? We compressed the gas, so we had to exert energy, namely work. So resetting the particle's position, erasure, costs work, a thermodynamic resource. At first glance, information and energy seem to have nothing to do with each other, but they turn out to be inextricably bound up. What if we add quantum physics to this mix of information and energy? Well, suppose that we want to erase not a classical bit of information, but a quantum bit, a qubit, basic unit of quantum information. We can encode a qubit in an electron, such as Audrey's electron from a few minutes ago. Well, Audrey's qubit can be entangled with Baxter's qubit in some fixed temperature environment. Remember, if Audrey's particle is entangled as strongly as possible, and then she measures her qubit, the outcome is totally random. She has no idea whether she'll obtain a 1 or a 0. So Audrey's qubit resembles the gas particle bit, whose location, right or left, 1 or 0, is totally random. Just as we could erase the gas particle bits, Audrey can erase her qubit. In fact, Audrey can erase her qubit while gaining work that she can use to fill a battery or lift a tiny weight. This result should surprise us because we just concluded that erasing information costs work. The trick is to sort of burn the correlations between the qubits. So entanglement serves as a kind of thermodynamic fuel in the presence of heat. So quantum phenomena can serve as resources in thermodynamics, in gaining work, as well as in information processing, in erasing information. if we gaze into the future of quantum steampunk, what do we see? Well, first, I believe that quantum thermodynamics will spread. Just as quantum information science has transformed other fields, such as thermodynamics, we're using quantum thermodynamics as a toolkit to understand black holes and chemistry and materials anew. Second, quantum thermodynamics has its roots in theory. It's provided fundamental insights, such as what separates quantum from classical physics, or what it means for time to flow. But experiments are growing in quantum thermodynamics, testing the theory and sparking new theory. A third opportunity is to make quantum thermodynamics practical in the spirit of the Industrial Revolution. For instance, I'm working with experimentalists in Sweden on a quantum refrigerator for cooling quantum computers. Quantum thermodynamics is an incredibly exciting emerging field. It's vibrant and growing. It offers both fundamental insights and technological possibilities. We can read about steampunk in novels, but this genre of science fiction is coming to life at the intersection of quantum physics, information science, and thermodynamics. So the fantasy of steampunk is becoming a reality. Thanks, and I'd be happy to take questions.
Dr. Yunger Halpern, that was just fantastic. I think that was an excellent both overview of the field that you study and the couple of chapters that we read. So just really wonderful introduction. Before we get too far into questions, a lot of students tend to ask us about, quantum is such an interdisciplinary field, and I think you talk about this a little bit in the prologue, but because it is such an interdisciplinary field and there's so many different ways you could get started, could you kind of provide some insight for students on what your introduction to quantum or maybe quantum thermodynamics more specifically kind of looked like, so they can learn about that as well?
Sure. I just need to take a moment. I have a cold at the moment, so I need to blow my nose. So I'm going to turn the camera and microphone off for just a minute, but I'll be back.
No worries. And students, I'm sure that you'll have lots of questions. If you have any questions at all, feel free to drop them in the chat, and I'll be pulling out a couple as we continue for the rest of the 30 or so minutes that we have left.
Okay. Yes, one reason why I love quantum information and quantum thermodynamics is that it is interdisciplinary. And I always wanted to study everything. So I didn't even want to pick a major in college. So I found some faculty who helped me get a well-rounded view of physics. I took a bunch of physics classes and some math, philosophy, and history related to physics and called that a major. I'd always had philosophical inclinations, but it was really a history of physics class that gave me the indication that it was physics that I should go into deeply, because I really enjoyed getting the historical perspective. The other students in the class were non-physics students, so I enjoyed interacting with them. I just saw that they interacted with the material differently because I had come across some of the topics before in actual physics courses, and so I could tell that I understood them more mathematically. And so I really wanted to understand the rest of the ideas just as thoroughly or more thoroughly. So that's what led me into physics. I'd say that within physics, quantum information captured me because it's at an unusual border between the fundamental and the practical. So on the one hand, we're now using quantum information to understand the nature of time and space and causality. So what's more fundamental than that? And I've always loved metaphysics, understanding the nature of the universe. On the other hand, I like the idea, and I think that's important for its own sake, but I felt that I would have an easier time justifying to myself what I was doing if I could also argue more easily that it was practical and useful. And as I said, quantum computers have the opportunity to transform fertilizer production. What is more useful than that?
Absolutely. And I don't think that's that specific example It's something that we've talked about before in any of our classes or programs. So that was a really excellent example that just impacts so much of our lives and that we kind of don't even really think about, right? In the food production cycle. My next question that a lot of students are always wondering about is, what does your day look like as a theoretical physicist? Like, how much time do you get to spend working in a lab versus writing like books like this versus doing, other sorts of experiments as well?
Yeah, as a theoretical physicist, I do partner with experimentalists. So I get to propose experiments and then try to convince labs to perform them. And then we work out how the experiment would be performed. They perform the experiment, they have problems, they ask us about the problems, we try to reconcile them together, and we analyze all the data together and write our papers together. I like to start reading a paper basically as soon as I get up, although nowadays, since I have a bunch of students and postdocs and lots of collaborators, there are usually lots of emails for me to read as soon as I get up. And in the morning, I like to spend the morning on my really hard work. So I could be analyzing some students' results nowadays. When I was a student, I was producing more of the results in first person, so to speak. I might also write papers and so synthesize a lot of information, do data analysis in the mornings. Then in the afternoons, I try to schedule my meetings. I'll meet with collaborators, postdocs, students, and we could be planning projects, troubleshooting projects, analyzing data together, planning papers. I give a lot of talks. A lot of them are technical. Like this morning, I gave a seminar for a biophysics group, actually, because even though most of biophysics is classical, still biophysicists care a lot about thermodynamics. And I find it really useful to learn from them about what they're doing in classical thermodynamics. And so I try to structure my day in that way. So I get to do my really tough thinking in the morning when I'm fresh and I have a lot of energy. And then in the afternoon, since I'm very collaborative, I love interacting with a lot of people, I try to do my interactions and my writing up of notes after meetings then.
That's awesome. And that sounds like a very well-rounded day too, get a little bit of everything. My other question is, what inspired you to write this book? Like it seems like at least like the content that I read seems like a pretty general introduction while still giving you the kind of nitty gritties of quantum steampunk and providing that technical introduction as well. So if you just want to talk a little bit more about kind of why did you choose to write this book?
I wrote it really because I'm a child of the liberal arts and sciences, the whole shebang. On the one hand, I'm a scientist, so I'm really, really, really excited about my research, and I think it's the most interesting thing in the world. So I wanted to share about that research. And on the other hand, as someone who's steeped in the liberal arts, I love how this field has the aesthetic of steampunk, which is a genre of literature, art, and film. So I wanted to share the delight of a scientific field that could be seen to interface with many different other fields that are, in a sense, across a border. So I would say it's that combination of science and the liberal arts.
That's awesome. I really loved how you used Aubrey and Baxter's story and like little vignettes to really introduce and demonstrate the problems you're going to be talking about in the chapter. That was just, it's such a cool, I'm an English major, and so I was an English major, so it was cool to see that kind of those two fields kind of marry in a really cool way. My final question before I start pulling from students is you talked a little bit about kind of what the future of quantum steampunk could look like. Could you tell students kind of what are your favorite applications that you see, or maybe the most near-term ones as well that you look forward to?
So far, the field has been largely foundational and fundamental. We've been learning about the separation between quantum and classical and sharpening the laws of thermodynamics and generalizing them. The field was also traditionally very theoretical, but it's increasingly become experimental. Now it's going to take another step to make it actually practical and applicable. And I think that the community right now is just starting to pivot in that direction. For instance, so the there really are very few examples, which I think is in part a great opportunity. But one is an experiment that I'm working on with collaborators in Sweden. They're experimentalists, and they are building a quantum computer of the sort in that giant refrigerator that I showed. And once they run a computation, they have qubits that are already cold because they're in the fridge. But at the end of a computation, the qubits need to be cooled down even further. And we're working on a quantum refrigerator for performing that extra cooling step inside of the classical refrigerator. And that quantum refrigerator is a quantum thermodynamic technology. And our initial simulations suggest that this quantum refrigerator actually might be quite competitive with some of the current technologies. So it would be a quantum refrigerator that services a quantum computer.
Awesome. That's super cool. We talked a little bit about hardware, and so I think that would be a really awesome tool that would help us advance, kind of all of these fields together. Aman in the chat asked, I think you might have touched on this a little bit during chapter 5, but they're curious, does the second law of thermodynamics apply to particles at the quantum level, or are there instances in which the second law is broken? If you want to answer that one a little bit.
For background, the second law of thermodynamics can be phrased in multiple ways. It states that the entropy of any closed isolated system either increases or remains constant, but does not decrease. And that is basically a statement that time flows in just one direction. People initially thought that quantum systems might be able to get around the second law of thermodynamics, but to my knowledge, there are no systems known to break the second law of thermodynamics. There are a number of paradoxes that initially look as though they might break the second law of thermodynamics, but if you analyze them more closely, then you find that they really obey it. Also, there are some ways that a system could bend around the second law of thermodynamics so that it doesn't really obey the assumptions on systems that should obey the second law. For instance, these systems could access certain quantum resources that cause them to be just in a slightly wrong setting, so the second law doesn't really apply. So that initially it looks like the second law is being broken and this is all very surprising, but then you find, oh, there are quantum resources that make this not quite obey the right assumptions. For a concrete example, suppose that we have a heat engine. In a classical heat engine or a quantum heat engine setting, we have two different environments at two different temperatures. And then we have an engine that sits between the two. Heat will flow from the hotter system to the colder system through the engine, and the heat will take some of that energy and use it to perform work, to do something useful. So suppose that we have a quantum engine here, and the engine can interact with two environments that, in a sense, look thermal, but they're actually in some special quantum states. So they share some properties of thermal systems. So they're kind of arguably thermal, but they're not really, because they actually have quantum coherence. But this engine can, well, if you have an ordinary heat engine with just two different environments at two different temperatures, then you can calculate its efficiency, and its efficiency always obeys a certain upper bound. And if any engine were to break that upper bound, then we would say that the second law of thermodynamics was broken. And this engine, this quantum engine that I just described, can break that bound. It's just those environments aren't exactly just simple thermal environments. So it kind of looks as though the second law is broken, but it isn't really, because the environments are not quite such that the second law should really apply. So I actually find it kind of amazing that the laws of thermodynamics are still going strong, even though they were devised for big classical systems.
Super interesting, and thanks for that clarification as well. We have lots of students in the chat who are interested in And I think you talked about this as well with, your interdisciplinary nature and wanting to, major in everything when you were in college. And so many students want to find ways now that they've learned and had this introduction to quantum steampunk to tie it into the areas that they're studying, like biotechnology and the biological sciences, others who are interested in computer science and cybersecurity. So in your opinion, what would be potentially even some like good classes for students to be taking in college, or ways to continue learning about the field?
Definitely a good statistical physics class. And statistical physics classes are offered in many different departments, so physics and chemistry and engineering. I definitely recommend taking one of those, maybe the one, whichever is offered by the best lecturer. I was advised in college to take classes for the lecturer rather than the topic. And that can provide a good broad foundation. And I suggest some ordinary quantum physics and also quantum information, which provides a different perspective than ordinary quantum physics classes do.
Awesome. I hope that's helpful for those that are asking as well. Vaithian asked in the chat, they really loved the book that they've read, that they've gotten to read so far. Yeah, they're wondering if you have plans for, is this going to be part of a series, or if there's other topics that you're going to explore further after?
Maybe it depends on where my research goes. We'll see. I do blog every month, so that is writing that is definitely going to continue. So I write for Quantum Frontiers, which is the blog of the Institute for Quantum Information and Matter at Caltech. So I'll definitely continue with that. A number of people have asked me if I'm going to write a novel, because as you mentioned, there are little snippets from an imaginary novel at the beginning of each chapter. And I have to say, I do think that in another universe, there is a copy of me that is a novelist. So I kind of suspect that I will end up writing novels at some point, but no concrete plans quite yet.
That's awesome. We have, sorry, a lot of questions came in at once. So I was like, oh, I'm sure that they loved the fact that they're looking forward to your novel. Yeah, let me go through. There's a few questions that I'm not sure what this question is asking, but they ask, are there any laws in quantum thermodynamics that particles follow like classical thermodynamics? Oh, actually, that's an interesting question. Are there quantum thermodynamics laws that you're kind of discovering or that are already in place?
Yeah, we can take the laws of thermodynamics that were formulated either decades or over a century ago and reformulate them so that they explicitly apply to quantum systems and information processing systems. So we do that using the language of, in part, quantum information theory. And the community has also found that these laws can be sort of enhanced or made more detailed when we think about, well, thermodynamics was developed for, again, large classical systems in which there are lots and lots of particles, and most of them more or less act like the average. Also, these systems are often in equilibrium, which is a rather boring state in which large scale properties like energy and volume and pressure remain constant, and there's no net flow of anything like particles into or out of the system. So we can extend the laws of thermodynamics away from that really simple picture to small systems, just a few particles, and systems far away from equilibrium, and find more detailed versions of the laws, or versions of the law, or let's say fine grainings of the laws that give us more information. For instance, an example consists of fluctuation relations, which are talked about in chapter 9 of the book, or discoveries in resource theories, which are maybe chapter 11.
A couple students are interested in what you were speaking about, the biophysics group that you mentioned. I think a little bit ago, you mentioned that you had given a lecture this morning. Do you want to provide a little bit of insight into kind of the intersection of those two thermodynamic fields? I think that would interest a lot of students.
Sure. So this talk was about a classical study. So I worked with actually a group of biophysicists. I was the weird one out from quantum information theory, but I think we're all interested in thermodynamics and information. The idea is that when we're pushed far from our comfort zones, then we can learn a lot. And you might think that this characteristic belongs to just humans or even, say, intelligent animals such as dolphins, but it turns out that there are really simple systems of just classical particles that can learn what pushes them out of equilibrium. Like there are even rafts formed from soap bubbles. So that there's this sort of circle of soap bubbles, and you can rotate the outer wall that surrounds the raft so that the raft gets stressed. And the raft comes to recognize, if you stress it through the same amount many, many times, then the raft comes to remember that distance through which it's been stressed. And you can read out the soap bubble's memory of that stressing by measuring its strain. So there are these really, really simple systems that can learn, I think, surprisingly a lot about the environments that push on them. And people have been using, over the past several years, thermodynamic signatures to learn about what these systems can learn about their environments. Like people will measure the work that one of these systems absorbs, and the amount of work that the system absorbs reflects how well the system remembers what's pushing on it. Which is nice. Just thermodynamics was developed a long, long time ago for systems that are not being pushed hard, but are in this very simple, boring equilibrium state. And in the meantime, we have learned a lot about the act of learning from computer science, from machine learning. So with some folks at MIT, I applied the toolkit of machine learning to figure out, or to measure, to detect this learning by these simple systems, and to detect the learning and to measure the learning more precisely, more thoroughly, and more accurately than with simple thermodynamic measures like how much work one of these systems absorbs. These materials are relevant to biophysics. Biophysicists also are interested in systems of many classical particles that are experiencing crazy environments, like some warm, wet pond that is being struck by lightning. So I presented about this intersection of thermodynamics and information theory. Maybe at some point we could try to discover similar behaviors in quantum systems of many, many particles.
Awesome. That was super cool. Lots of students are interested in biological applications of quantum, and then also seeing how to explain the biological world with quantum. So I think that that's a really, really exciting intersection of interest, especially of students.
Mm-hmm.
I have about 15 minutes left, and I think our questions have slowed down by quite a bit. So before I ask our last question, is there anything else that you'd like to share with students, either about your book, about your experience, about the research that you do in the lab, or the research that you do? Yeah, I'll give it to you.
I would say that quantum information theory and quantum thermodynamics are really exciting fields to be in. They're growing a lot. They have a lot of energy. They fortunately have a lot of support. There's a lot of room. So I hope that you join. Quantum thermodynamics in particular is in a position that quantum information theory was a number of years ago, as in it's an emerging field, it's establishing itself. So there are a lot of opportunities, and it is a lot of fun.
Awesome. That is a great answer to my last question, but we did have a student who asked, I think, a bit more of a technical question. Jamie asked, can you tell us about uncomplexity and where it fits into triumvirate of thermodynamics, informational science, and quantum physics?
That sounds like the question came from a recent paper of mine. So I Sorry, just a minute. I should have a drink for my voice.
Yeah, no worries. It sounds like they did their pre-reading.
Yeah, this topic was emerged from the study of black holes. I, again, do love reaching across disciplinary boundaries. So I like talking with people in high energy theory and string theory who are thinking about black holes and what implication those have for, say, the universe's preservation of information. But the way that I think about complexity from a thermodynamic perspective is, suppose that you have a whole bunch of particles, say a whole bunch of atoms that are interacting with each other in some typical way. So the neighbors, two neighbors will talk to each other, two other neighbors will talk to each other. And this, the way that the interactions spread out information is a little bit random. It's kind of chaotic, usually. So you can think about a system like this as thermalizing in many, many stages, or coming to equilibrium in many, many stages. And as we said, equilibrium is that relatively boring stage in which nothing much is really happening. In contrast, when you talk about an analogous system that is classical, there's more or less just one stage. So suppose that you have a gas of classical particles in a box. And suppose that all of the gas particles begin clumped together in one corner of the box. They're not in equilibrium because soon they're going to spread across the box. Their volume is going to increase a whole lot. But once they've spread across the box, there's not really anything else for them to do. They've reached equilibrium. So there's more or less just one stage. But the analogous situation in quantum physics is more complicated. And coming to equilibrium, to this very quiet stage where everything interesting is over with, basically, that takes longer and has multiple stages. So suppose that we have this whole bunch of particles, bunch of atoms, let's say, interacting with each other, exchanging information, maybe exchanging energy. The first stage of equilibrium is, if you look at just one little atom all by itself, then it'll look like, after a very short while, it'll look quiet. Things don't change very much for that atom. But then suppose that instead of just looking at one atom, you look at correlations all across the system. Those correlations or quantum information take longer to quiet down to some steady state. And then suppose that you wait even longer than what we call complexity reaches equilibrium. But what is complexity? Suppose that we're interested in some quantum state psi, some pure state. Suppose that you're preparing it on a quantum computer, let's say. So you start off with a quantum computer with a bunch of qubits in some fresh state, a bunch of that we often represent with a 0, for those who are familiar with the notation. And then we perform a whole bunch of quantum gates to prepare some state psi. So what is the minimum number of gates that we need to prepare the state? That's called the complexity of the state. And we can also think of the state as being prepared by starting off with all of these atoms in the all zero state and then just letting them interact randomly. Then they will inherently prepare some interesting, complicated quantum state. And the number of basic operations that you need to prepare the states will grow and grow and grow for a really, really long time, and then flatten out. So finally, the system will reach complexity equilibrium. Now, a lack of complexity, closeness to the 0 state, is useful in quantum computation, because when we start off a quantum computer, we give it an all 0 state. It's like clean scrap paper on which the computer can write its calculations. So a lack of complexity, uncomplexity, is useful as a resource. So that's how uncomplexity comes to be in quantum thermodynamics.
A fantastic answer, and just Jamie, what a great question too. That really arrives at, I think, everything that we've been talking about so far. So I have one final question, and I know that we also want to take a group photo. So maybe while Dr. Yunger Halpern answers this last one, if folks want to turn on their cameras and just get ready to smile in a couple minutes, we'll be taking a group photo. But the question that we always leave with when we invite in guest speakers is if you could kind of summarize advice to share with students who are just beginning their quantum journey or who might only be a year or two into exploring quantum, what would you share?
I would say have fun. You probably won't have fun every minute because integrals are difficult and papers are difficult to decipher. And so the path is difficult, but at some course grain level, hopefully, I hope that you're having a lot of fun, because in doing science, we get to pursue our curiosity and just keep learning and not stop learning. So I think it's a wonderful opportunity, and I hope that on the whole, you are having fun, and I encourage you to pursue fun in your quantum studies.
What a great answer. This was certainly for me a fun hour. And so hopefully you all continue to come to seminars like this and continue to, if you're interested in quantum thermodynamics or quantum steampunk, definitely, read the rest of Dr. Yunger Halpern's book. It's fantastic. I'm going to do one last call to turn on your cameras. I think a few people are still joining. I'm looking down because I'm on a different device and I'm going to take the photo on, but maybe on the count of 3, I'll grab a couple of screenshots. Oh, there comes everyone. Hey, y'all. Okay, and sorry, had a bit of an echo, but 1, 2, 3. And 1, 2, 3. Okay, for the last one, I gotta say something cheesy. Everyone say quantum thermodynamics. Perfect. Thank you so much, everyone, for coming. Dr. Yunger Halpern, for just a really fantastic last hour. Everyone, if you want to say thank you in the chat, we'll wish everyone and a great rest of your day, afternoon, evening, wherever you're calling in from. We'll see you later.
Thanks so much for the conversation.
All right. Bye, everyone.
I'm muted. Do you need anything else from me?
No, I think we're good. That went really well.
Yeah, I was like monitoring it. And I was like, but thank God there's nothing.
Yeah. All right. I'll see you later. Have a good night.
You too.
Bye.